February 1991, a spacecraft named Magellan was circling Venus, firing radar pulses through the planet's impenetrable clouds, mapping a world no human eye could ever see. On one of those orbits, it captured an image of a volcanic vent, a nearly circular pit, less than a square mile across, with steep interior walls and traces of ancient lava spilled down its slopes. 8 months later, Magellan passed over the same spot. The vent had changed. It had nearly doubled in size. The walls had collapsed. Something had filled it almost to the brim. For 30 years, that image sat in NASA's archives. Nobody noticed. And then, in 2023, a planetary scientist named Robert Herrick did something remarkable. He started looking. What he found would change everything we thought we knew about Earth's so-called sister planet. And it was only the beginning. Because Venus isn't just geologically alive. Something else is happening in those sulfuric acid clouds. Something that, even now, scientists cannot explain. This is a story about discovery and mystery, about a planet we thought we understood and realized we didn't. It's about the scientists who spent decades ignoring their closest neighbor, only to find that neighbor had been hiding something extraordinary. And it's about a question that has haunted researchers since the space age began. Could there be life on Venus? The answer, as it turns out, is not as simple as we once believed. Before we go further, you need to understand what Venus actually is, not what you think it is. Not the romantic evening star that ancient Romans named after their goddess of love, the real Venus. Venus is hell. The surface temperature averages 867 degrees Fahrenheit, hotter than Mercury, despite being nearly twice as far from the sun. Hot enough to melt lead, zinc, and tin. Hot enough that if you could somehow transport an unprotected human to the Venusian surface, they would be dead before they had time to register the heat. The air itself would scald you. But the temperature is just the beginning. The atmospheric pressure at Venus's surface is 92 times that of Earth's, equivalent to being 3,000 feet underwater in our planet's oceans. If you could somehow survive the temperature, you would be crushed. The atmosphere isn't just heavy. It's so dense that the carbon dioxide at the surface isn't technically a gas anymore. It's a supercritical fluid, a strange state of matter with properties of both liquid and gas, 6.5% the density of water. You wouldn't just be standing in Venus's atmosphere. You would be swimming in it. And that atmosphere would kill you in another way too. The clouds that perpetually shroud Venus are composed of sulfuric acid droplets, the same corrosive substance used in industrial processes to dissolve metals and strip organic material. Rain falls from those clouds, but it never reaches the surface. The droplets evaporate in the intense heat long before they touch down, only to rise and condense again in a hellish cycle that never ends. The Soviet Venera landers that touched down in the 1970s and 1980s transmitted images for minutes, sometimes an hour at most, before the heat and pressure destroyed them. These missions were extraordinary achievements of engineering and determination. Venera 9 and Venera 10, which landed in 1975, returned the first photographs ever taken from the surface of another planet. The images showed a landscape of flat, angular rocks under an orange sky. The light of the sun filtered through Venus's thick atmosphere, scattered into a perpetual amber twilight. Venera 13 and Venera 14, which landed in 1982, took color photographs and even recorded sound, the first audio recordings from another world, microphones captured the whistle of Venusian wind, the hiss of the corrosive atmosphere against the lander's hull. Then, after about 2 hours, the transmission stopped. The landers had been destroyed. Those grainy photographs remain to this day our only direct glimpse of the Venusian surface. They show a landscape that looks ancient and still and utterly dead, a world baked and crushed into submission by its own atmosphere, a cautionary tale of what happens when climate runs out of control. For decades, that was the scientific consensus. Venus was dead, geologically, biologically, in every way that mattered. The planet had experienced some catastrophic volcanic event hundreds of millions of years ago that resurfaced the entire globe, erasing its history. And then it went quiet. A cautionary tale of runaway climate change, frozen in time. Then Robert Herrick started comparing pictures. The Magellan spacecraft was one of NASA's most successful planetary missions, though few people remember it today. Launched from the Space Shuttle Atlantis in May 1989, it arrived at Venus in August 1990 and immediately began what would become the most comprehensive survey of another planet's surface ever conducted. Magellan's secret weapon was synthetic aperture radar, a technology that uses radio waves to peer through clouds and darkness and construct detailed images of terrain below. Unlike visible light, radar doesn't care about Venus's perpetual cloud cover. It punches straight through, bounces off the rocky surface, and returns with information about what's down there. Over 4 years, Magellan mapped 98% of Venus at resolutions between 100 and 300 meters, good enough to see individual volcanoes, lava flows, and impact craters. What it revealed was a world dominated by volcanism. Venus has more volcanoes than any other planet in the solar system, possibly as many as 1,600 major ones, with tens of thousands of smaller vents and domes scattered across its surface. Shield volcanoes like Mat Mons and Sapers Mons tower miles above the surrounding plains. Vast lava fields stretch for hundreds of kilometers. Pancake domes, strange flat-topped structures found nowhere else, rise from the terrain like geological mushrooms. The mission ended in 1994 when Magellan was deliberately plunged into Venus's atmosphere to gather final measurements of atmospheric density. The spacecraft disintegrated, its silicon and metal returning to the void from which it had observed so much. But its data survived. Terabytes of radar imagery stored on magnetic tapes and optical discs, waiting for someone to look at them with fresh eyes. Herrick is a research professor at the University of Alaska Fairbanks and a member of NASA's Veritas mission team. In 2021, when NASA announced that Veritas would be one of its next Venus missions, Herrick felt inspired to revisit the Magellan data. The old spacecraft had mapped 98% of Venus's surface between 1990 and 1992, creating a database of radar images that remained the most detailed views of Venus ever captured. The problem was, Magellan's data was designed for mapping, not for monitoring change. The spacecraft orbited Venus at different angles on different passes, which meant comparing images from different times was maddeningly difficult. A feature that looked different in two images might simply appear that way because the radar was hitting it from a different direction. Herrick knew he was looking for a needle in a haystack, with no guarantee the needle even existed. He spent more than 200 hours manually comparing images. "I didn't really expect to be successful," he later admitted, and then he found it. The volcanic vent in question sits on the northern flank of a massive shield volcano called Mat Mons. in a highland region near Venus's equator called Atla Regio. Mart Mons rises 5 miles above the surrounding terrain, higher than Mount Everest above sea level. It had long been suspected of volcanic activity, but suspicion is not proof. The February 1991 image showed a circular vent, less than a square mile across, with steep walls and evidence of old lava flows. The October 1991 image showed something dramatically different. The vent had expanded to an irregular shape of about 1.5 square miles. The walls had shortened, collapsed inward, and the pit appeared to be nearly filled to its rim with something. Herrick knew he had to be careful. Radar images can be tricky. The same feature can look different when viewed from different angles, and the two images had been taken from different orbital passes. A skeptic might argue that the apparent changes were just geometric illusions. The vent hadn't actually changed, it just appeared different because the radar was looking at it differently. To rule out this possibility, Herrick contacted Scott Hensley, a radar specialist at NASA's Jet Propulsion Laboratory and one of the world's leading experts on interpreting synthetic aperture radar data. Hensley had spent decades debunking false alarms in planetary radar imagery, cases where researchers thought they'd found something exciting, only to discover it was an artifact of the viewing geometry. Together, they built computer models of what an unchanged vent should look like from the second viewing angle. They ran simulations, tested different scenarios, tried to find any explanation other than actual surface change. The models didn't match. The only explanation that fit the data was that something real had happened on Venus between February and October 1991. An eruption, a lava lake forming, walls collapsing as magma withdrew. Volcanic activity. Only a couple of the simulations matched the imagery, Hensley said, and the most likely scenario is that volcanic activity occurred on Venus's surface during Magellan's mission. While this is just one data point for an entire planet, it confirms there is modern geological activity. The scientists estimated that the eruption at Mart Mons was similar in scale to the 2018 eruption of Kilauea volcano in Hawaii. A significant event, but not an outlier by terrestrial standards. Venus's volcanoes, it seemed, behaved much like Earth's. The study was published in the journal Science in March 2023. For the first time in history, scientists had direct visual evidence of an active volcano on Venus. We can rule out that it's a dying planet, Herrick told reporters. But that was just the first discovery. Venus, it seemed, had more secrets to share. The scientific community took notice. If Herrick had found one eruption by examining less than 2% of Magellan's coverage area, how many more might be waiting in the rest of the data? Researchers around the world began re-examining the old images with new techniques and fresh perspectives. In May 2024, a team of Italian researchers led by Davide Sulcanes of D'Annunzio University in Pescara announced they had found more. Using a different technique, analyzing changes in radar backscatter rather than visual vent shapes, they identified volcanic activity at 2 additional locations. Sif Mons, another shield volcano in a region called Isla Regio, and the western part of Niobe Planitia, a volcanic plain. The radar signal strength had increased along certain paths between 1990 and 1992, suggesting new rock had formed. The researchers estimated the Sif Mons eruption produced about 30 square kilometers of new rock, enough to fill 36,000 Olympic-sized swimming pools. The Niobe Planitia eruption produced even more, 45 square kilometers, enough to fill 54,000 pools. For comparison, when Mauna Loa erupted in Hawaii in 2022, Earth's largest active volcano, it produced enough lava to fill 100,000 pools. By analyzing the lava flows we observed in 2 locations on the planet, Sulcanese said, we have discovered that the volcanic activity on Venus could be comparable to that on Earth. This was no longer a single data point. Venus was volcanically active, with eruptions occurring frequently enough that 3 separate events were captured during a 2-year observation window. Scientists began revising their estimates of how often Venus erupts, from once every 10,000 years to every few months, similar to Hawaii's Big Island or the Canary Islands. The implications went far beyond simple geology. Volcanoes aren't just interesting in themselves. They're windows into a planet's interior. When magma rises from the deep mantle and erupts onto the surface, it brings information about the conditions below, the temperature, the composition, the dynamics of heat flow that drive geological processes. On Earth, volcanic activity is intimately connected to plate tectonics. Most of our volcanoes occur at plate boundaries, where oceanic crust dives beneath continental crust, subduction zones, or where plates pull apart, mid-ocean ridges. The few volcanoes that occur away from plate boundaries, like Hawaii, are thought to be fed by deep mantle plumes, columns of hot rock rising from near the core mantle boundary. Venus doesn't have plate tectonics in the Earth sense. Its surface appears to be a single, continuous shell of rock, what geologists call a stagnant lid. Without plate boundaries, Venus's volcanoes must be fed by different mechanisms. Understanding those mechanisms could reveal how Venus loses its internal heat, how its mantle convects, and whether any form of tectonic activity is occurring beneath that frozen crust. The volcanic discoveries also had implications for Venus's atmosphere. Fresh volcanic eruptions release gases, sulfur dioxide, water vapor, and others, that can affect atmospheric chemistry for years afterward. The sulfuric acid clouds that shroud Venus are maintained by sulfur compounds, and volcanic activity is almost certainly a major source. If Venus's volcanoes are erupting frequently, they could be continuously resupplying the atmosphere with reactive gases, maintaining the chemical disequilibrium that makes Venus so puzzling. But the volcanic discoveries raised a deeper question. If Venus was geologically alive, churning with magma and spewing lava onto its surface, what did that mean for the planet's history? What did that mean for its atmosphere? And what exactly was producing the strange chemical signatures that decades of observations had failed to explain? To understand why Venus matters, you have to understand how close it came to being Earth. Venus is almost exactly the same size as our planet, 7,521 miles in diameter, compared to Earth's 7,918. Its mass is 81.5% of Earth's. It's made of the same rocky stuff, formed from the same primordial dust cloud around the same young sun about 4.6 billion years ago. It has a metallic core, a silicate mantle, and a crust of basaltic rock. If you were an alien astronomer observing our solar system from a distant star, you might reasonably conclude that Venus and Earth were twins, 2 siblings born together, destined for similar fates. They are not, and the story of how they diverged is one of the most important tales in planetary science. The question that haunts planetary scientists is, why not? For most of the 20th century, scientists assumed Venus had always been hostile. Its proximity to the sun, they thought, had prevented water from ever condensing on its surface, Venus was born hot and stayed hot, a world that never had a chance. But starting in the 1970s, evidence began to accumulate that the story was more complicated. NASA's Pioneer Venus mission detected an unexpectedly high ratio of deuterium, heavy hydrogen, to ordinary hydrogen in the Venusian atmosphere, a ratio about 150 times higher than on Earth. This was a crucial clue. Deuterium is heavier than regular hydrogen, which means it escapes into space more slowly. If Venus once had abundant water, and that water was gradually stripped away by solar radiation over billions of years, you would expect to see exactly this kind of deuterium enrichment in whatever water remained. Venus, in other words, might once have been wet. Current theories suggest that early Venus may have looked remarkably like early Earth. In 2016, researchers at NASA's Goddard Institute for Space Studies used climate models to simulate Venus's ancient history. Their results suggested that Venus could have had liquid water oceans and habitable surface temperatures for as long as 2 to 3 billion years, longer than life has existed on Earth in its current complex forms. Michael Way, the lead author of that study, found that if Venus had a slow rotation rate like it does today, one Venusian day lasts 243 Earth days, and if it had more dry land in the tropics than Earth does, it could have maintained surprisingly moderate temperatures despite receiving more sunlight. The slow rotation would have created a thick layer of clouds on the day side that reflected incoming solar radiation, acting as a natural umbrella. These results show ancient Venus may have been a very different place than it is today, Way said. The question then is what happened? And here, we enter territory that is both scientifically fascinating and disturbingly relevant to our own world. The prevailing theory involves something called a runaway greenhouse effect. At some point, possibly around 700 million years ago, possibly earlier, something changed. Perhaps massive volcanic eruptions released enormous quantities of carbon dioxide into the atmosphere over a geologically short period. Perhaps the oceans began to evaporate as the sun grew brighter with age. Perhaps the two factors combined. Or perhaps there was something else entirely, some trigger we haven't yet identified. Whatever the cause, a feedback loop began, and once it started, it couldn't be stopped. Rising temperatures caused more water to evaporate. Water vapor is a greenhouse gas. More of it in the atmosphere trapped more heat. More heat caused more evaporation. The cycle accelerated. Each step made the next step more likely, more inevitable. Eventually, the oceans boiled away entirely. Not metaphorically, literally. The water that once may have covered Venus's lowlands, that might have supported early chemistry or even early life, was transformed into steam and rose into the atmosphere. The planet's entire water budget was suspended in the sky. But the atmosphere couldn't hold it. As the water vapor reached the upper atmosphere, ultraviolet radiation from the sun began tearing the molecules apart, splitting them into hydrogen and oxygen atoms. The hydrogen, being the lightest element, escaped into space, accelerated by the solar wind. Over millions of years, Venus bled its hydrogen into the void. The oxygen bonded with iron on the surface or was consumed by other chemical reactions, locked into rocks and minerals where it remains today. Without water, there was no rain. Without rain, there was no weathering of rock, the process that on Earth slowly absorbs carbon dioxide from the atmosphere over geological time. The CO2 accumulated year by year, millennium by millennium. The pressure rose, the temperature skyrocketed, and Venus became what it is today, a crushing, suffocating, broiling oven of a world. The transformation was probably complete within a few 100 million years. By cosmic standards, that's the blink of an eye. A world that might have been habitable for billions of years was rendered permanently hostile in less time than complex life has existed on Earth. Earth avoided this fate, barely. If our planet had formed a few percent closer to the Sun, we might have gone the same way. And as our Sun continues to brighten over billions of years, Earth's own oceans will eventually boil. In a sense, Venus is a preview of Earth's distant future. But Venus is also a warning about Earth's present. The carbon dioxide that turned Venus into a furnace is the same gas we are pumping into our own atmosphere. Venus doesn't tell us Earth will become a hothouse. Our planet is too far from the Sun for that, at least on any human timescale. But Venus does tell us what happens when greenhouse gases run out of control. It is a planet-sized experiment in the physics of climate catastrophe. And now, we know that Venus isn't finished. Its volcanoes are still erupting, still pumping sulfur and other gases into its atmosphere, still shaping a world we barely understand. Which brings us to the mystery. Scientific breakthroughs sometimes come from expected places, from well-funded laboratories with state-of-the-art equipment, from NASA missions designed to answer specific questions. But sometimes they come from left field, from researchers asking questions that nobody thought to ask, looking for things that nobody expected to find. In September 2020, an astronomer named Jane Greaves made an announcement that sent shockwaves through the scientific community. Greaves, a professor at Cardiff University in Wales, had been studying Venus's atmosphere using two of the world's most powerful radio telescopes, the James Clerk Maxwell Telescope, JCMT, in Hawaii, and the Atacama Large Millimeter Array, ALMA, in Chile. She was looking for something specific, a molecule called phosphine. On the face of it, this might seem like an odd choice. Phosphine is a simple chemical compound, one phosphorus atom bonded to 3 hydrogen atoms, chemical formula pH3. On Earth, it's a foul-smelling, toxic gas associated with decaying organic matter, swamps, marshes, sewage, penguin guano. It's colorless, flammable, and lethal to humans at concentrations above about 50 parts per million. Not exactly the kind of molecule that screams important scientific target. But here's the thing. On Earth, phosphine is almost exclusively produced by life. Bacteria in oxygen-poor environments, like the mud at the bottom of ponds or the guts of certain animals, generate it as a metabolic byproduct. Industrial processes can make it too, of course, but in nature, phosphine is a biological signature. In 2019, a team at MIT, led by Clara Sousa Silva, had published a paper arguing that phosphine could serve as a biosignature, a chemical indicator of life on other worlds. On rocky planets like Earth or Venus, they argued, there are no known non-biological processes that can produce phosphine in significant quantities. Lightning doesn't do it. Volcanoes don't do it. Meteorite impacts don't do it. If you found phosphine in the atmosphere of a rocky planet, it would strongly suggest something was alive. Greaves found phosphine on Venus. The detection was tentative, about 20 parts per billion, a trace amount high in the Venusian atmosphere. But it was there, in a region where no known chemical process should be producing it. The original research team, which included scientists from MIT, exhaustively analyzed every possible non-biological explanation they could think of. They found none that worked. "It's very hard to prove a negative," said Clara Sousa Silva, a research scientist at MIT who had done the original biosignature work on phosphine. "We have done everything we could think of to explain this detection without life." The announcement made global headlines. Had we found evidence of alien life on Venus? The answer, it quickly became clear, was maybe, but also maybe not. And the story of what happened next is a lesson in how science actually works. The messy, contentious, uncertain process by which we distinguish truth from error. Within weeks, other scientists began pushing back. The initial reaction in the scientific community was skepticism, not hostility, but the healthy caution that greets any extraordinary claim. Extraordinary claims require extraordinary evidence, as Carl Sagan famously said, and the evidence for phosphine on Venus was still preliminary. Some researchers challenged the detection itself, arguing that the spectral signature Greaves had identified might actually be sulfur dioxide, a common Venusian gas, rather than phosphine. The two molecules absorb radio waves at similar frequencies, and distinguishing between them requires careful analysis. Could the Cardiff team have made a mistake in their data processing? Others noted that follow-up observations by different telescopes failed to find the molecule at all. If phosphine was present at 20 parts per billion, as Greaves claimed, it should have been detectable by other instruments. Why weren't they seeing it? NASA's SOFIA Airborne Observatory, a telescope mounted on a modified Boeing 747 that flew above most of Earth's water vapor to get clearer views of space, searched for phosphine in Venus's atmosphere over 3 flights in November 2021. Martin Cordner of NASA's Goddard Space Flight Center led the effort, carefully targeting the same atmospheric region where the original detection had been made. They found nothing. According to their results, if phosphine was present at all, it was at most 0.8 parts per billion, far lower than the original claim, and arguably consistent with zero. Phosphine is a relatively simple chemical compound. It's just a phosphorus atom with 3 hydrogens, so you would think that would be fairly easy to produce, Cordner explained. But on Venus, it's not obvious how it could be made. The implication was clear. If there wasn't any phosphine to explain in the first place, there was no need to invoke exotic chemistry or life. The scientific community was divided. Some dismissed the phosphine detection as a processing error or a case of mistaken identity. Others argued that the negative results from different telescopes simply reflected the fact that different instruments probed different altitudes and times, and that phosphine might vary across the Venusian atmosphere. Perhaps it was concentrated in certain regions and absent in others. Perhaps it fluctuated over time, present during some observations and gone during others. Greaves and her colleagues didn't give up. They knew their data. They believed in their analysis. And they understood that scientific progress doesn't come from walking away from controversy. It comes from gathering more evidence, refining methods, addressing criticisms head-on. They continued observing, accumulating more data, refining their analysis. The James Clerk Maxwell Telescope in Hawaii became a dedicated Venus monitoring station, tracking changes in the planet's atmospheric chemistry over months and years. And in July 2024, at the Royal Astronomical Society's National Astronomy meeting in England, they presented new findings. The phosphine was real, they argued. 4 years of additional observations had strengthened the evidence. More intriguingly, the phosphine levels appeared to fluctuate with Venus's day-night cycle, rising at night, falling during the day, as if sunlight was destroying the molecule and something else was continuously replenishing it. All that we can say is that phosphine is there, said Dave Clements of Imperial College London, part of the observing team. We don't know what's producing it. It may be chemistry that we don't understand, or possibly life. They also announced something new: tentative evidence of ammonia, another gas that on Earth is primarily produced by biological or industrial processes. The debate is far from settled. A 2024 paper in Frontiers in Astronomy and Space Sciences, co-authored by several of the original Discovery team members, acknowledged that the source of phosphine on Venus remains an unsolved problem. They reviewed every proposed non-biological mechanism: photochemistry, lightning, volcanic outgassing, meteorite delivery, and found none adequate to explain the observations. The title of their paper was blunt: Source of Phosphine on Venus, an Unsolved Problem. And phosphine isn't even the oldest mystery. Since at least the 1920s, astronomers have known that something strange is happening in Venus's upper atmosphere. When observed in ultraviolet light, the planet reveals dark patches and streaks, regions where something is absorbing UV radiation that would otherwise be reflected back into space. The first observations of these features came from ground-based telescopes nearly a century ago. Frank Ross at Mount Wilson Observatory photographed Venus in ultraviolet light in 1927 and noticed unusual dark markings that moved across the planet's disk. The patterns were clearly atmospheric. They shifted and changed over timescales of days, but their cause was completely unknown. Nearly 100 years later, it still is. These dark markings are prominent enough to influence Venus's weather. They absorb more than 50% of the solar energy reaching the planet. They move with the 4-day super-rotation of Venus's upper atmosphere, winds that blow at over 200 miles per hour, circling the planet 60 times faster than the surface rotates below. Whatever is creating these patterns is being generated somewhere, transported across the globe by hurricane-force winds, and dispersed. Some force or process is continuously producing the absorbing material, because photochemistry and atmospheric mixing should break it down over time. And after a century of study, scientists still don't know what it is. The phenomenon is called the unknown UV absorber, and that name tells you everything you need to know about our state of knowledge. V.A. Krasnopolsky of the Catholic University of America, who constructed the first photochemical model for Venus's upper atmosphere, wrote in 2021 that there is no general agreement on the nature of the UV absorber in Venus, and thus this remains one of the most intriguing open questions in planetary atmospheres. Researchers have proposed dozens of candidates over the decades: ferric chloride, various sulfur compounds, elemental sulfur, disulfur monoxide, disulfur dioxide, even organic carbon compounds dissolved in sulfuric acid. Each proposal explains some aspects of the observations, but fails to account for others. The absorber has the wrong spectrum, or it doesn't match the observed distribution in the atmosphere, or it should be destroyed too quickly by photochemistry to explain the persistent patterns. In 2018, a team led by scientists at Justus Liebig University and Soochow University conducted laboratory experiments on sulfur-oxygen compounds and announced that certain isomers of S2O2 match the spectral characteristics of the UV absorber. In 2024, researchers at the University of Cambridge synthesized iron-bearing sulfate minerals under conditions mimicking Venus's clouds and argued that a combination of rhomboclase and acid ferric sulfate could explain the patterns. But there's another possibility, one that dates back to 1963, when a young astronomer named Carl Sagan published an article in the journal Nature. What if the UV absorber is life? Sagan proposed that microorganisms living in Venus's cloud layer could be using ultraviolet light as an energy source, a kind of alien photosynthesis. The idea seemed outlandish at the time, and it still sounds outlandish today. How could anything survive in sulfuric acid clouds? How could life evolve in an environment so different from Earth's? And yet the proposal has never been definitively ruled out. The persistence of the life hypothesis isn't just wishful thinking or science fiction enthusiasm. It reflects a genuine epistemic problem. We don't fully understand Venus's atmospheric chemistry. The observations show anomalies that existing models can't explain. Some of those anomalies are consistent with biological activity, not conclusively so, but consistent. Consider the facts. Venus's atmosphere contains gases that shouldn't be there. Phosphine, if the detections are real, has no known abiotic source. Ammonia has been tentatively detected by multiple probes, even though it should be rapidly destroyed by the acidic environment. The vertical distribution of sulfur dioxide doesn't match photochemical models. Oxygen has been measured in the lower atmosphere at levels that are hard to explain. Large non-spherical particles exist in the lower cloud deck, and no one is sure what they are. Any one of these anomalies might have an innocent explanation: unknown chemistry, measurement error, incomplete models. But taken together, they suggest that something unusual is happening in Venus's atmosphere, something we don't understand. The conservative interpretation is that our models are incomplete. Venus is a complex chemical environment, and we've only scratched the surface of its atmospheric processes. Given enough time and better data, scientists will probably find ordinary explanations for all these phenomena. But there's another possibility, one that scientists are trained to consider, even if they don't consider it likely. The anomalies could be connected. They could be signatures of a single phenomenon that produces multiple effects. They could be signs of life. The reason is simple. Venus's clouds are one of the few potentially habitable environments in the inner solar system outside Earth. Yes, the surface is unsurvivable, but about 30 miles up, conditions change dramatically. At an altitude of roughly 50 to 60 kilometers, the atmospheric pressure drops to about 1 Earth atmosphere. The temperature ranges from 86 to 158 degrees Fahrenheit. Hot, but within the range of some extremophile organisms on Earth. Thermophilic bacteria thrive in hot springs at temperatures above the boiling point of water. Acidophilic microbes flourish in environments with pH levels below 3. The radiation environment at this altitude is similar to Earth's surface. The atmospheric pressure is breathable. Gravity is about 90% of Earth's. In some ways, this zone of Venus's atmosphere is more hospitable than anywhere on Mars. Of course, there's the matter of the sulfuric acid. The clouds themselves are composed primarily of sulfuric acid droplets, which sounds lethal, and probably is. Sulfuric acid is one of the most corrosive substances known. It will dissolve organic material, attack most metals, and destroy virtually any biological structure it comes into contact with. Any life form attempting to survive in the Venusian clouds would face an acid bath that would kill essentially every known organism on Earth. But some researchers have proposed creative solutions. Hypothetical Venusian microbes could survive inside the droplets by maintaining a neutral internal environment, protected by acid-resistant membranes. On Earth, some extremophile bacteria have evolved to live in highly acidic conditions by pumping protons out of their cells faster than the acid can force them in, maintaining an internal pH that would be lethal in the surrounding environment. Could Venusian life have evolved similar defenses, perhaps even more extreme ones? There's another challenge. The cloud droplets don't stay at habitable altitudes forever. As they grow and accumulate, they become heavy enough to sink toward the hotter depths below. Eventually, they evaporate entirely, only to recondense higher in the atmosphere. Any organism living inside a droplet would be carried downward into lethal heat, destroyed along with its home. But Sarah Seeger of MIT and her colleagues have proposed a life cycle that could work around this problem. When the droplets grow too heavy and begin to sink, the organisms inside could desiccate, dry out, and enter a dormant state, like the spores of certain bacteria on Earth. These desiccated cells would be small and light enough to remain suspended in the lower haze layer, waiting. Eventually, atmospheric convection would loft them back up to cooler altitudes, where they would encounter water vapor and rehydrate, beginning the cycle again. A perpetual cycle, living life in the thin, habitable band of a planet that otherwise offers only death. Is this likely? Probably not. Most scientists believe the UV absorber will eventually be explained by mundane chemistry. But the history of science is full of phenomena that seemed purely physical until they turned out to be biological, or vice versa. Until we send probes into Venus's atmosphere to sample the clouds directly, we cannot rule anything out. And the missions are coming. For more than 30 years, Venus has been largely ignored by NASA. The last American spacecraft to visit the planet was Magellan, which ended its mission in 1994. In the decades since, NASA has sent multiple rovers to Mars, dispatched probes to Jupiter and Saturn and Pluto, and landed on asteroids and comets. Venus, despite being closer to Earth than any of these destinations, was passed over again and again. The reasons were partly scientific. Mars had water ice and ancient riverbeds that hinted at past habitability, while Venus seemed utterly hostile to life. They were partly technical. The Soviet Venera missions had demonstrated how difficult and expensive it was to explore Venus's surface, while Mars offered a relatively benign environment for long-lived rovers. And they were partly cultural. Mars had captured the public imagination in a way that Venus never did. But in 2021, NASA finally changed course. The agency selected 2 Venus missions as part of its discovery program, DAVINCI and Veritas. After decades of neglect, humanity was going back to Earth's evil twin. NASA's DAVINCI mission is scheduled to launch in June 2029. Its name stands for Deep Atmosphere Venus, Investigation of Noble Gases, Chemistry and Imaging, an acronym chosen to honor Leonardo da Vinci, the original polymath, known for his aerial sketches and scientific curiosity. Da Vinci will do something no NASA mission has done since 1978. Send a probe into Venus's atmosphere. And unlike the pioneer Venus probes of that era, DAVINCI will carry instruments capable of detecting the very molecules that have made Venus so mysterious. The mission architecture is ambitious. A carrier spacecraft called CRIS, Carrier Relay Imaging Spacecraft, will fly by Venus twice, imaging the planet's clouds and mapping surface emissivity in infrared light. During these flybys, cameras and spectrometers will study the upper atmosphere, tracking the movement of clouds, analyzing the composition of the haze layers, and searching for signs of the mysterious UV absorber. Then, on a third approach scheduled for June 2031, CRIS will release a spherical descent probe about 3 feet in diameter. The probe will enter the atmosphere at roughly 25,000 miles per hour, protected by a heat shield until it reaches an altitude of about 42 miles. Then the shield will be jettisoned and the real science will begin. As the probe descends through the clouds, it will sample the atmosphere continuously, analyzing noble gases, trace chemicals, and isotope ratios that can reveal Venus's history. Noble gases like helium, neon, argon, and xenon are particularly valuable because they don't react chemically. They preserve information about conditions billions of years ago, offering clues about where Venus's atmosphere came from and how it evolved. By comparing Venus's noble gas composition with that of Earth and Mars, scientists can begin to understand why these 3 similar planets ended up so different. DAVINCI will also look for Phosphine, its Venus tunable laser spectrometer, based on the same technology that detected organic molecules on Mars with the Curiosity rover, will measure trace gases with unprecedented sensitivity. If phosphine is present in the Venusian atmosphere at the levels some researchers have claimed, DAVINCI should find it. And if it's not there, or if it's present at much lower concentrations, that will be equally important information. The probe will also measure sulfur compounds that might indicate volcanic activity. Fresh volcanic eruptions release sulfur dioxide and other sulfur-bearing gases into the atmosphere. By measuring these compounds and their distribution, DAVINCI can help determine whether Venus's volcanoes are still active and how much they're contributing to atmospheric chemistry. About 100,000 feet above the surface, the probe will clear the clouds and begin photographing the terrain below, the first direct images of Venus's surface in more than 40 years. Its target is Alpha Regio, a highland region featuring so-called tessera terrain, complex, highly deformed rock formations found nowhere else in the solar system. If Venus ever had continents, the tesserae may be their remains. The tesserae are among the most enigmatic features on Venus. They cover about 8% of the planet's surface and appear as intensely fractured and folded terrain, with ridges and grooves running in multiple directions. Under radar, they look almost biological, like the wrinkled surface of a brain or the bark of an ancient tree. Their complexity suggests a violent geological history, with multiple episodes of compression and extension, creating overlapping patterns of deformation. Some scientists believe the tesserae are ancient, predating the volcanic plains that cover most of Venus's surface. If so, they could preserve chemical and mineralogical evidence of an earlier era, possibly even an era when Venus had water. Others argue that the tesserae are still forming today, created by active tectonic processes that we don't fully understand. Either interpretation would be revolutionary. If the tesserae are ancient, they offer a window into Venus's past that has been erased everywhere else on the planet. If they're still forming, They suggest that Venus has some form of plate tectonics, something scientists have long debated, which would make it far more geologically interesting than anyone imagined. DAVINCI's descent into Alpha Regio will provide the first close-up data on tessera chemistry and mineralogy. The probe's infrared cameras will be able to identify rock types that can't be distinguished from orbit. If the tesserae contain granite-like rocks, for example, that would suggest they formed in the presence of water, possibly indicating ancient oceans. If they're purely basaltic, like most of Venus's plains, the story would be different. The probe will continue transmitting data until it reaches the surface, and possibly a few seconds beyond, though it's not designed to survive. Within minutes, the heat and pressure will destroy it, as they destroyed every Venera before. But unlike the Venera landers, which had to store data locally and transmit it in real time through Venus's thick atmosphere, DAVINCI will relay its information to the CRIS spacecraft orbiting overhead, ensuring that nothing is lost. By then, we will know things about Venus we have never known before. NASA's other Venus mission, Veritas, has had a more troubled path. Originally planned for launch in the late 2020s, it was delayed in 2022 due to institutional problems at JPL related to the Psyche asteroid mission. The delay pushed the launch date to no earlier than 2031, and for a time, the mission's funding was cut so drastically that observers called it a soft cancellation. But Veritas has powerful advocates, including its principal investigator, Suzanne Schmecker of JPL. She and her colleagues argued that a 2029 launch was still achievable with modest additional funding, and that the science case for the mission was stronger than ever given the recent volcanic discoveries. In late 2023, a congressional committee endorsed Schmecker's position, and the mission's prospects improved. Veritas will carry state-of-the-art synthetic aperture radar capable of mapping Venus's surface at far higher resolution than Magellan ever achieved, 30 meters versus 100 meters, and will measure surface topography with 5-meter vertical accuracy. This isn't just an incremental improvement, it's a transformation. At 30-meter resolution, scientists will be able to see individual lava flows, fault scarps, and volcanic vents. They'll be able to track changes in the surface over time, searching for fresh eruptions and active tectonic features. Veritas will also carry the Venus Emissivity Mapper, VEM, built by the German Aerospace Center, which will use infrared spectroscopy to determine what Venus's surface is made of. By measuring how different rock types emit thermal radiation, VEM can distinguish between basalts, granites, and other compositions. Information that's crucial for understanding Venus's geological history. If Venus once had continents like Earth, its surface composition should reflect that. If plate tectonics ever operated there, we should see evidence in the rock types. Perhaps most importantly, Veritas will be able to watch for volcanic eruptions in real time. By comparing radar images taken months or years apart, scientists can detect surface changes caused by fresh lava flows, exactly the kind of evidence that Robert Herrick found in the Magellan archives. But while Herrick had to laboriously compare low-resolution images taken 8 months apart, Veritas will produce high-resolution maps of the entire planet on a regular basis, making it far easier to spot volcanic activity. These new discoveries of recent volcanic activity on Venus provide compelling evidence of the kinds of regions we should target with Veritas when it arrives at Venus, Schmrekar said after the 2024 volcanic findings were announced. Evidence for activity, even in the lower resolution Magellan data, supercharges the potential to revolutionize our understanding of this enigmatic world. The European Space Agency is also preparing its own Venus mission, Envision, scheduled for launch in 2031. Envision will study the coupling between Venus's interior, surface, and atmosphere, seeking to understand how the planet evolved from a possible ocean world to the inferno it is today. It will carry a synthetic aperture radar similar to Veritas's, developed in collaboration with JPL, as well as spectrometers to study atmospheric composition and surface properties. Together, DAVINCI, Veritas, and Envision will provide the most comprehensive study of Venus ever attempted. They'll investigate the planet from multiple angles: surface, atmosphere, interior, and from multiple vantage points: descent probe, radar mapper, atmospheric analyzer. Whatever Venus has been hiding, these missions will find it. And there are others. India's ISRO has proposed a Venus orbiter mission called Shukrayan-1, which could launch in the late 2020s. Russia has discussed reviving its Venera program with a mission called Venera-D. A private venture called Morning Star Missions, backed by Rocket Lab, has proposed sending small probes into Venus's atmosphere on an accelerated timeline. After decades of neglect, during which Mars received mission after mission while Venus was ignored, the second planet from the Sun is finally getting the attention it deserves. The next decade will see more spacecraft visit Venus than in the previous 30 years combined. But why does Venus matter? The obvious answer is scientific curiosity. Venus is a puzzle, a world that should be Earth's twin, but became something radically different. Understanding why Venus went wrong could teach us about planetary evolution, atmospheric chemistry, volcanic dynamics, and perhaps even the origins of life. But there are deeper answers too. Answers that connect Venus to questions about our own world, our own future, and our place in the cosmos. The first deeper answer is about planetary habitability. For centuries, astronomers have speculated about life on other worlds. In recent decades, we've discovered thousands of exoplanets orbiting distant stars, and we've identified hundreds that might be roughly Earth-sized and roughly the right temperature for liquid water. But we don't know which of these worlds are actually habitable. We don't know what separates a planet that can nurture life from one that can't. Venus and Earth offer a natural experiment. Two planets, nearly identical in size and composition, formed from the same primordial material at nearly the same distance from the same star. And yet one became a paradise, and one became a furnace. Why? If we can answer that question, if we can understand exactly what factors tipped Venus over the edge while Earth stayed habitable, we'll know something profound about the requirements for life in the universe. We'll be able to look at distant exoplanets and make better predictions about which ones might harbor biology. We'll understand, in a way we don't now, how special Earth really is. The second deeper answer is about us. Earth and Venus formed from the same raw materials, at roughly the same distance from the same star. They are almost exactly the same size. They have similar densities, similar compositions, similar internal structures. By all rights, they should have followed similar evolutionary paths. They didn't. One became a garden, one became a furnace, and we still don't fully understand why. This matters for practical reasons. If we can understand what triggered Venus's runaway greenhouse effect, we might better understand the limits of Earth's climate system. We might learn what feedback mechanisms pushed Venus past the point of no return, and whether similar mechanisms could ever threaten our own world. But it matters for philosophical reasons too. Venus is a reminder that habitability is fragile, that the conditions we take for granted on Earth, liquid water, moderate temperatures, breathable air, are not cosmic defaults. They are the result of specific circumstances, specific histories, specific accidents of planetary evolution. A world can look like Earth and become something utterly different. We are the first species in the history of Earth capable of understanding this. We can look at Venus and see our own alternative future, a path not taken, a fate narrowly avoided. We can recognize that the planet we call home is special, precious, and vulnerable in ways our ancestors never imagined. That recognition carries responsibility. If Venus teaches us anything, it is that planetary environments can change irreversibly, that greenhouse gases have consequences, that feedback loops, once triggered, can spiral beyond control. These are not abstract lessons. They are written in 867-degree rock under sulfuric acid clouds, 26 million miles away. Venus isn't a prediction for Earth. Our planet is too far from the Sun, and even the most extreme climate projections don't suggest we'll become another Venus anytime soon. The carbon dioxide concentration in Earth's atmosphere is about 0.04%. Venus's is 96.5%. Even if we burned every fossil fuel on the planet, we couldn't approach those levels. The physics of climate on Earth are different enough that a true runaway greenhouse, the kind that would boil our oceans, is probably impossible in the next several billion years until the Sun brightens enough to trigger it naturally. But Venus is a proof of concept. It demonstrates that a rocky planet similar to ours, in the habitable zone of its star, can undergo catastrophic, irreversible climate change. It shows what happens when positive feedback loops overwhelm negative ones, when the system tips past a point of no return. It proves that planets can die. More immediately, Venus demonstrates that greenhouse gases work exactly as physics predicts. They trap heat, they warm surfaces. They can transform a temperate world into a furnace. The specific mechanisms that produced Venus's 867-degree surface temperature, the accumulation of CO2, the loss of water, the cessation of chemical weathering, are different from the mechanisms driving climate change on Earth. But the underlying principle is the same. When we pump carbon dioxide into our atmosphere, we are performing an experiment. The experiment has been done before, on a planetary scale, with results that are clearly visible to anyone with a telescope. We can see the outcome, hanging in the evening sky, the brightest star that isn't a star. In a sense, Venus is a message from physics itself. This is what happens when the greenhouse effect wins. And there's one more reason Venus matters. In the search for life beyond Earth, we have historically focused on Mars, a cold, dry world that may have been habitable billions of years ago but shows no signs of present-day life. We have studied the ice moons of Jupiter and Saturn, where liquid water oceans may exist beneath frozen crusts. We have scanned the skies for signals from distant civilizations around other stars. We have mostly ignored the planet next door. Venus is closer to Earth than Mars. Its atmosphere, however hostile, is far more substantial than the thin wisp surrounding the red planet. Its clouds, whatever else they may be, provide chemical complexity and energy gradients. If life can exist in the crushing depths of Earth's ocean trenches, in the boiling pools of Yellowstone, in the sulfuric acid environments of volcanic vents, if life can find a way in conditions we once thought impossible, then perhaps we should not be so quick to write off the clouds of Venus. The Phosphine mystery remains unsolved. The UV absorber remains unidentified. The chemical disequilibrium in Venus's atmosphere remains unexplained. These may all have purely physical explanations. Probably they do, but probably is not certainly. And until we send probes into those clouds to sample them directly, we cannot know. In 2025, scientists at Cardiff University proposed a new mission concept called VERV, Venus Explorer for Reduced Vapors in the Environment, a small probe that could hitch a ride on ESA's Envision spacecraft and survey the Venusian atmosphere for phosphine, ammonia, and other potential biosignature gases. The mission would be modest in cost and scope, but its potential payoff would be extraordinary, because if there is life on Venus, even microbial life, even the simplest possible form of biology, it would change everything. It would mean that life arises easily, whenever conditions permit. It would mean the universe is probably teeming with living things. It would mean we are not alone. And if there isn't life on Venus, that would be significant too. It would tell us that even when a planet starts out similar to Earth, even when it has water and warmth and energy, life is not guaranteed. It would make Earth more precious, more improbable, more worth protecting. Either way, Venus has something to teach us. There's a tendency, when we think about space exploration, to focus on what we might find, the discoveries, the breakthroughs, the definitive answers to ancient questions. But sometimes the most valuable thing about exploration isn't the finding, it's the looking, the act of paying attention to something we've ignored, the discipline of asking questions even when we're not sure we'll like the answers. For decades, Venus was the forgotten planet, too hostile for rovers, too close for mystery, too familiar for excitement. We sent mission after mission to Mars, looking for signs of ancient water and fossilized microbes, while Earth's closest neighbor rotated slowly under its acid clouds, keeping its secrets. Now we know that Venus was never the dead world we assumed. Its volcanoes still erupt. Its atmosphere still churns with chemicals we can't explain. Its clouds may or may not harbor life, but they certainly harbor mysteries, puzzles that have resisted explanation for longer than most of us have been alive. And in the coming decade, we're finally going back. DAVINCI will descend through those sulfuric acid clouds, sampling gases that may have remained unchanged for billions of years, photographing terrain that no human eye will ever see directly. Veritas will map the surface in unprecedented detail, watching for fresh lava flows and volcanic eruptions that could be happening even as the spacecraft orbits overhead. Envision will study the coupling between Venus's interior, surface, and atmosphere, trying to understand how a world so similar to Earth became so radically different. These missions won't answer every question. They'll probably raise new ones. That's how science works. Each discovery opens doors we didn't know existed, reveals ignorance we didn't know we had. But they'll tell us something true about Venus, and by extension, something true about ourselves, about the fragility of habitable worlds, about the power of greenhouse gases to transform a planet, about the possibility that life, once it arises, might find ways to persist even in conditions we consider impossible. Robert Herrick spent 200 hours staring at grainy radar images from a spacecraft that finished its mission before most of today's graduate students were born. He was looking for evidence that something had changed on Venus, some sign that the planet was not frozen in time. The geological processes were still at work beneath those sulfuric clouds. He found it, a volcanic vent that doubled in size in 8 months, proof that Venus is alive. Since then, scientists have found more eruptions, more lava flows, more evidence of a world in geological motion. They have detected hints of phosphine, hints of ammonia, hints of chemistry that no one can explain. They have proposed missions that will descend through Venus's atmosphere for the first time in decades, sampling gases and photographing terrain that no human will ever see with their own eyes. Venus was supposed to be a dead world, a cautionary tale, a warning about what happens when a planet's climate runs out of control. Scientists had written it off, moved on to more promising targets. Mars had water ice, Europa had a subsurface ocean, Titan had organic molecules, Venus had nothing but heat and acid and crushing pressure. Or so we thought. It turns out Venus is a lot more complicated than that. It is active, dynamic, mysterious. It holds secrets we have barely begun to uncover. Its volcanoes still pour fresh lava across its surface. Its clouds still harbor unexplained chemistry. Its atmosphere still defies our models. And perhaps most remarkably, Venus is still capable of surprising us. After more than half a century of space exploration, after hundreds of papers and thousands of observations, we discovered in 2023 that we had been wrong about something fundamental. The planet we thought was geologically dead is geologically alive. The world we thought we understood was hiding in plain sight. What else don't we know? We have spent decades looking at Mars, searching for fossils of ancient microbes that may have lived billions of years ago. We have spent decades listening to the radio spectrum for signals from distant civilizations that may not exist. All that time, Venus was right there, closer than Mars, wrapped in clouds that might contain the first evidence of extraterrestrial life ever discovered. Or might not. We don't know. That's the point. The honest truth is that we have no idea whether Venus harbors life. The phosphine detections remain controversial. The UV absorber probably has a mundane chemical explanation. The atmospheric anomalies that some researchers find suggestive can likely be explained by geochemistry, photochemistry, or volcanic processes we don't fully understand. But here's what's remarkable. We can't rule it out either. After decades of study, after hundreds of papers and thousands of observations, we cannot definitively say that Venus's clouds are lifeless. The hypothesis remains viable. And as long as it does, Venus will continue to beckon us. Because if we're wrong about Venus, if there is something living in those clouds, something that has found a way to survive in an environment we consider hostile beyond imagination, then everything we think we know about life in the universe changes. We have assumed, perhaps unconsciously, that Earth is special, that our planet hits some cosmic jackpot, that the conditions for life are rare and precious and unlikely to be repeated. We've searched for biosignatures on distant exoplanets, wondered about microbes beneath the ice of Europa and Enceladus, speculated about intelligent civilizations orbiting other stars. But in all that searching, we've treated our own solar system as mostly understood, mostly explored, mostly mapped. Venus reminds us that isn't true. The world next door still has secrets. The morning star still has questions we can't answer. The missions are being built. The launches are scheduled. The probes will descend through acidic clouds into crushing heat toward a surface that glows with the temperature of a pizza oven. They will measure gases that haven't been directly sampled since the 1980s. They will photograph terrain that no human being has ever seen clearly. And they will send back data that will either solve the mystery or deepen it. Perhaps they will find that Venus's atmospheric anomalies have mundane explanations, that phosphine was a measurement error, that the UV absorber is simply iron sulfate, that the chemical disequilibrium reflects nothing more exotic than volcanic outgassing and photochemistry. That would be a valuable result, even if disappointing. It would tell us that Venus is merely a dead world with active geology, fascinating but not revolutionary. Or perhaps they will find something else, something unexpected, something that challenges our assumptions about what is possible on a hellish world wrapped in sulfuric acid clouds, something that makes us reconsider what we think we know about life in the universe. Either way, Venus will never be the same. The planet that ancient Romans named for the goddess of love, that generations of stargazers watched rise and set without knowing what it was, that scientists dismissed as a cautionary tale and moved on from. That planet has been hiding secrets. Some of them we have discovered. Others are still waiting. Venus has always been there, bright in the evening and morning sky, beautiful and unreachable. The ancient Romans named it for the goddess of love. The ancient Babylonians called it Ishtar, goddess of the morning and evening star. The Maya tracked its movements with extraordinary precision, building their calendars around its appearances. Cultures around the world have watched it rise and set, marveled at its brilliance, never knowing what lay beneath those shining clouds. For most of human history, Venus was simply a light in the sky, the brightest point in the heavens after the sun and moon, beautiful, mysterious, unreachable. Then we built rockets, we sent probes, we fired radar through the clouds and mapped a world of fire and acid. And for a while, we thought we understood. Venus was dead. Venus was simple. Venus was a warning, nothing more. Now we know better. Venus is alive. Venus is complex. Venus has secrets we are only beginning to uncover. Now we are about to find out what else it has been hiding. And whatever the answer turns out to be, Venus will never look the same again. The next time you see Venus in the twilight sky, a brilliant white point of light, brighter than any star, remember what it is. Not a peaceful evening star, not a romantic symbol, a world of fire and acid, of volcanoes that still erupt, of chemical mysteries that still defy explanation. A planet that was supposed to be dead and isn't. A place that might, against all odds, harbor something we never expected to find. Remember that we are going back. Remember that the probes being built today will descend through sulfuric acid clouds and sample gases that haven't been measured directly in nearly half a century. Remember that orbiters will map the surface in unprecedented detail, watching for fresh lava flows and volcanic eruptions. Remember that for the first time since the space age began, we are treating Venus as a priority, not an afterthought. And remember that in a universe full of wonders, the strangest one might be the world next door. We thought we knew Venus. We thought it was dead. We thought it had nothing left to teach us. We were wrong.